Welcome student in this microwave lab. I am Chhabilal Singh, working as assistant professor in Soviet University Meerut, and today we will learn how to make a bench setup for the study of magic T, and also calculating the scattering parameter of magic T. So let's start. This is the block diagram of magic T, and this is my whole bench setup, and you can see here this knob is set in current. This is voltage and this is ripple voltage. So this current is increasing gradually, and it will becomes above 50 milliampere. Here you see milliampere. Then you can see here square wave will come. Yes, make it this. So okay, and this knob for here you can see AM for square wave, and this FM for sawtooth wave, FM modulation, amplitude modulation, CM continuous wave. This is external for external testing, and these two knobs for FM setting the amplitude and frequency, and these two knobs for setting the amplitude of AM modulation and frequency. This is this knob used for beam voltage, this knob used for ripple voltage. So beam voltage we can use from 240 to 400 volt DC, and this we can use from 10 volt to 270 volt. So this beam voltage we will set around 270 or 30 volt, and this ripple voltage 150 or 170, like this. So already we have set all these parameters initially, and this standby means only heater filament supply is on. So here you can see this actually, and this is slatted section. With the help of this you can vary, and this is frequency meter. So see, this is the square wave appear on CRO. So this is cathode ray oscilloscope, and CRO wave appear there, and this is Klystron power supply, and this is Klystron tube. This is fan for cooling purpose. Switch on this for cooling purpose. This is isolator. We are using this isolator for input or power. Whatever input we are applying, that only flow in only one direction. So we are using this isolator, and this is frequency meter, which capture the electric frequency which is flowing through this waveguide. This is variable attenuator, slatted section. We have a scale here, and this is my magic T. This is our magic T. So see, this is E-plane T, and this magic T is combination of E-plane and H-plane T, as you can see in this block diagram. And according to this block diagram, you can make the bench setup like this according to this block diagram. And here this is match termination. This is port 4, and this is H-plane, E-plane T here, and this is port 3, which is where we are applying the input. This is the E-plane T and H arm, and this is arm 1 and arm 2. We are getting the output from arm 2. This is detector mount. This is detector mount. Okay. So here is square wave. So by wiring this slatted line, you can find out the maximum and minima. So this is this you can see maximum, and you can slightly rotate this slatted section. Okay, and you can see the next maxima, and this is the next maxima. You can find out this one. This is this one 40, and rotate this another, and rotate. Yeah, this is one minima. This is a minima point is, this is 12 millimeter, and rotate again, and then yeah, see, this is another maxima point. This is 11.4 millimeter. Okay, and rotate again, and this you can, yeah, see, this is another minima. Its value is 10.4. okay, rotate this in oscillator section and find out another maxima. Yeah, see, this is another maxima, 9.4. so like this you can find out the maxima and minima, and with the help of this frequency meter you can slowly rotate, and you can see here dip on the wave, where you can find the dip on the wave until you can rotate this frequency meter, and we are trying to find out the frequency. Okay, rotate it. See the dip in CRO. Yeah, see here some dip. Yes, see, this is the dip here. Yeah, you can see this frequency meter, you can see dip here. Okay, at this point where we are getting the dip in my wave, from this point we are getting the dip in my wave. Yes, here we are getting the dip in my wave. So here we can see the frequency, these two horizontal line, between these two horizontal line and this vertical line intersecting which frequency, that is the that is my frequency. See here, it's a 9.92. this 9.92 gigahertz is my operating frequency. So like this you can find out the frequency, and you can here in Magic T, if we are find out like this scheduling parameter, you can find out like this. We have calculated this parameter. See here see this one. If H, E and H are perfectly matched, so S33 and S44 equal to 0. So H for symmetry property, you can see this like this. S1 S2, this is the scattering matrix, and putting the value in this symmetry property here, and you can find out the simplify this matrix, and you can find out your scattering parameter. And if port 3 and 4 are isolated to each other, then S3, 4 and 4 is equal to 0. And if we give input at port 3 HM, then output means electric field at port 1 and port 2 is same and in phase. So S13 is equal to S23 is equal to. So here we are applying the input in arm 3 means H arm, and we are taking the output from this port 1 or port 2 anywhere. So here we are getting taking the output port 2, and you can this match termination, you can just use this termination, and this match termination you can put here, and this detector mount you can put here, arm 4 as E arm, and you will take the output from here also. So like this you can measure the scattering parameter of your this Magic T, and see isolation also. You can calculate the isolation with the help of this VSWR meter. And coupling coefficient, we have mentioned the formula here. So this one port and I is the respecting the your here input, and J means output. And see here, if we give input at port 4 HM, then output it means electric field at port 1 and port 2 is same but out of phase. So like this you can calculate the parameters. So inside of this and this is your tunable probe, and inside of this electric field are flowing and detecting this one, and find out maximum and minima, and with the help of this frequency then get this barrier alternator. So thank you student, you can do yourself like this. Thank you.